Now next topic that is the dipole in a uniform magnetic field. Same in electrostatics also we discussed the electric dipole in uniform electric field. Now here we have to discuss the magnetic dipole in the uniform magnetic field. So when magnetic dipole is placed in the uniform magnetic field, so dipole means bar magnet, two poles are there, one is north, another one is south pole. Okay. So if it is placed at some angle with the magnetic field, then in the magnetic field, north pole and south pole will experience the forces in mutually opposite directions. In mutually opposite directions. And this couple means these two forces will equal in magnitude, opposite in direction, and not collinear, will produce the torque. So here the torque acts on the dipole when it is placed in the uniform magnetic field. So if it is at some angle theta, then torque acts on it, that is tau, that is equal to magnetic moment M cross magnetic field B. Magnitude wise torque, that is MB sine theta. Now under the effect of this particular torque, dipole will be rotated in such a way that theta decreases. It implies that we can say this thing here, the torque produced will rotate the dipole in the opposite direction of theta. And therefore here we have to introduce one negative sign. Okay. So under the effect of this torque, it will rotate so that theta decreases. Therefore, tau, that is minus MB sine theta. Now, if we take theta that is very small, then sine theta that is nearly equal to theta. So we can write tau that is equal to minus MB theta. Now in standard 11th, we studied this thing. Torque tau that is equal to I alpha, where I that is the moment of inertia, alpha that is the angular acceleration. So we can write torque tau that is I alpha that is equal to minus MB theta. But alpha, the angular acceleration, that is 2 time differentiation of angular displacement with respect to time t. So we can write I d2 theta by dt2 that is equal to minus mb theta. Now take I on right hand side. So we can write d2 theta by dt2 that is equal to minus mb upon I into theta. Now we can say this one is the differential equation for the motion of this bar magnet or magnetic dipole in uniform magnetic field. Now see, the form of this particular equation, that is exactly like the equation, differential equation of simple harmonic motion. The differential equation for the simple harmonic motion, that is d2y by dt2 equal to minus omega square y. So here from comparison of these two equations, we can say this thing: if dipole is placed at some angle with magnetic field and then if we release it, then dipole will execute simple harmonic motion, or we can say it will execute simple harmonic oscillations. Now, here if we compare these constants of the motion, then we can write omega square, that is equal to mb upon I. Therefore, omega, that is under root mb upon I. So this is the angular frequency for the simple harmonic oscillations of magnetic dipole in uniform magnetic field. Now, omega, that is 2 pi f, and that is equal to under root mb upon I. So we can write frequency of the oscillations f, that is 1 upon 2 pi under root mb upon I. So from this one, we can write the periodic time for the oscillation of the dipole, that is 2 pi under root I upon mb, because periodic time, that is 1 upon frequency. Clear to all of you?